inviting. Okay, cool. Again, I'm Justin, and I'll be starting at Berkeley as a PhD student in the fall. I'll be presenting some work I've been doing with Gabe and Jianan. And Jianan's also here to help me present, but unfortunately, Gabe was not available to present today. Yeah, cool. And Jianan is going to his second year PhD at Columbia. And we worked with Ronghui Gu and Suman Jana as advisors. And I'll let Jianan start off the talk.
Do you want to keep the screen share? And
yeah, I'll keep the screen sharing.
Okay.
Because we make sure there's no technical issues.
Hi everyone, I'm Jianan, and as Justin introduced, I'm a second-year PhD student here at Columbia University, working with Ronghui Gu and Suman Jana. And I'm very glad to start talking about our work on using continuous logic networks to solve loop invariants for program verification. And okay, next slide. So just give a little bit context about verification. So typically we have a program that it may be deployed in a critical software application. So if there is a bug, it has serious consequences. So one promising way to eliminate bugs is use formal verification. That is, we use a formally defined mathematical model to prove that our program is bug-free. Then, when it is deployed, it can guarantee that the software it uses is secure. And many aspects of verification can be done automatically. However, for loops, this can basically pose very difficulties for automatic verification. So there are different ways to deal with loops in program verification. And an easy way is to unroll them. So you give suppose there's a loop and you unroll it for 1,000 iterations. Then you can guarantee that within these 1,000 iterations, the loop is always correct. So in this way, the loop is bounded and you just treat it as straight execution of the program. This is typically adopted in many previous automatic verification tools, like here we list hyperkernel, NICO, and Servo, or use some sort of unrolling to prove programs with loops. And there's another kind of methods that gives a loop invariant, which is the formal definition of loop invariant will be introduced later, but it's an expression that is whole regardless of what iteration we are in. So using a loop invariant, we can formally verify that the loop is correct. And we don't need to assume that the loop terminates within, say, 1,000 iterations. And this is a more rigorous way to prove the program properties. This is using some of the previous works as SL4 and M30 These are formally verified OS kernels, and Perennial and Amada. These are latest works. And typically the loop invariant, say in all of the 4 works listed above, need to be provided by an expert. That is to say, you need to, the verifier needs to manually specify the loop invariant, which is often a very long and complex formula, and it requires intense manual effort. So our work is just to bridge this gap. So we want to automatically learn the loop invariant for formal verification so that we can have basically an end-to-end automatic verification framework. And I think Justin. Do you want to continue here?
Oh, sure. Okay. So just to really drive home, what is a loop invariant? consider this example we have here, which is just calculating the sum from 1 to k. So in the framing of a loop invariant, you're given some kind of precondition, something that you know definitely holds beforehand, and you know something you want to be true at the end, and that's sort of the goal is to prove that this is the case. And in this case in particular, you're saying that indeed at the end you really are getting the sum of the first k integers for x. And so the loop invariant in this case captures that and says that every incremental step that x will be equal to the sum of the first y integers, and then at the end you can conclude that y is equal to k, and then the proof goes through. So a loop invariant, formally speaking, is something that you know necessarily is true whenever the loop is starts being executed. Certainly it is true from one iteration to the next via some kind of induction argument, and then hopefully is strong enough to then conclude that the post condition holds. Just to give a motivating example of our work, consider I just sort of gave you this loop and asked for some kind of invariant to know for sure that t is equal to 0 at the end. Anyone sort of looking at it would have to pause and think about like really what's going on and whatnot. I mean, one thing you might want to do is to execute it and sort of see what you get. And in this case, you'll see that it sort of alternates and sort of traces out two different lines. And in fact, that invariant, that essentially captures the target variant that is necessary to prove this post condition, which is that the points either lie on the line above or the line below, and that is necessarily that u is less than 0. So using this intuition, we're sort of like building on a line of work that looks at this data-driven approach to loop invariant inference. In particular, you can like, what is the data in this case? Well, the data is essentially annotating the source code in order to get the execution state before anything happens, and then after each loop completes execution. And we know for these data points that the invariant should hold if it is indeed an invariant. So we'll collect the data, we'll get a bunch of training samples. And then it's sort of like a big picture how data-driven loop invariance works is you hand it some kind of candidate generator, and for this case, for example, guess the correct invariant right off the bat, then be able to hand it to SMT solver, which then can, once given the candidate invariant, check if it is indeed sufficient to prove the post condition. And the nice thing is that there's been a lot of work on the solving end and checking. And so that by and far, like generally speaking, works pretty well. And so our work really focuses on this candidate invariant generation. And so our work sort of improves on that slice. So in a big picture view, we're given some source codes, we generate execution traces, which serve as our samples, which we train our CLN model, which we'll go into more detail in a bit, which generates out an invariant. And then that downstream, it can be checked via a numerous number of tools, including Z3. Cool.
I have a question, if you don't mind.
Yeah, absolutely.
I was wondering if you're also targeting the generation of samples, the test cases themselves, or are you assuming you're given a fixed set of training data?
So for our work, that's what's being presented. We sort of just assume that we have a good set of data samples. But absolutely, if you're not, for example, like if you haven't seen one side of a branch or something like that, you're certainly not going to be able to get a good enough invariant. So we have some currently paused work that's sort of on the direction of whether you can sort of flip our design principles in order to essentially build what would be some kind of like buzzer that sort of like communicates with the invariant generation in order to sort of work hand in hand and be able to like recognize if you're missing data points. But that's a very good question.
Awesome, thanks.
Cool. If there are no more questions, I'll continue on. Cool, yeah. So in the next section, I'll talk about some of our key challenges. So the set of all invariants that we're possibly searching over is absolutely humongous. It's basically any combination of these like integer arithmetic units, in addition to like any like nesting of and and or. So it's like humongous space of potential invariance. So something that would be really nice is if we could basically learn in this space and search via gradient descent and take advantage of the advances in neural network technology. Unfortunately though, logic is discrete fundamentally. And so given this formula, it's either only going to be true or only going to be false based on the usual semantics, usual interpretation of the logic. And so our contribution, where it starts, is coming up with this relaxed logic, which will then allow us to essentially explore the space in this like partial truth interpretation. So go into more detail. For example, we have this function f, which is either true or false, either 1 or 0. And sort of generating a mapping so that it's now a smooth end function, which then we have some kind of interpretation, some kind of gradient that can guide us as we're searching for, trying to search along the space of formulas. So just to sort of give you a sense of why this makes sense, sort of mapping the problem to a machine learning problem, consider we're given the data points in orange, which represent this line that's with the slope of negative 0.5. And we want to essentially learn some kind of, and like this is a simplified example that is just considering learning the arithmetic part. And what you'll see is that if you start off with some random guess, the hope is that the neural network will know how to update the weights in order to get closer and closer to the ground truth model. And in this case, in blue here is modeling what the current guess is, which is guessing that it's over here. It's a guess that it's a weight of w equals 1 and v equals 0.5, which is essentially the slope of 2. And then here, given an output, what do we want to maximize? We want to maximize that wx plus vy after being given this like a Gaussian loss in a sense, that the values are as close to 1 as possible. So with each step, with each update, the line becomes closer to the ideal line, and then as you can see, like it'll based on the gradient move itself towards the something that's very close to the correct answer. Is there any questions with regard to that? Cool. So now I'll go into more detail. What exactly is this smooth end logic? So as a quick roadmap, this section is sort of long, so I'll try to keep it organized and clear as much as possible. We'll talk about first what's the semantics for the arithmetic clauses, and then we'll talk about the logic connectives, and then introduce how do we learn what the logic structure is, which I think is the most interesting part of this work, and then sort of give a big picture of what's going on. So first off, with the arithmetic clauses, a natural interpretation of greater than or less than would be something like a sigmoid. And an interpretation of the equality would be something like Gaussian. And in a sense, if I was given like a bunch of observations for x, and there was maybe, I don't know, like some kind of like deviation, like what's a very natural thing to assume is like some kind of like Gaussian fit over top. And what that sort of gives you, sort of looking back at the previous demo, is that if your line is not quite perfect, you'll get a little bit of deviation around 0, and then as a fit becomes better, eventually you'll get a perfect fit where everything fits right in the middle of the Gaussian. And then additionally, I want to note that to distinguish between x is greater than or equal to versus x is greater than, we can sort of shift the sigmoid by an epsilon amount in either direction. Cool. But the issue with this construction, though, is that what is the best fit? What will give you the value of 1 or the inequality would be just to drive everything to infinity. And like certainly that is true. To say that if x is greater than 0, certainly x is greater than negative infinity, right? So that sort of introduces a problem that we had to overcome, which is how do you handle finding tight inequalities? Because, for example, in this case, if you want to learn that a squared is less than n, then it's not sufficient just to have any line that certainly is true, but is not particularly useful at proving the postcondition. In particular, you want something, or in this case, we have something that is certainly true for loop executions, but not enough to prove the postcondition. Whereas if you're able to find that indeed a square is less or equal to n, then you're able to push all the way through to a postcondition, and it indeed is true for loop executions. So we need to make a small modification to how we interpret or represent the inequalities. And in particular, we add essentially a little bit of penalty for being far away from the inequality boundary. And you can see the full details in the paper. I won't go into that, but just to get a quick demo of what that sort of looks like. If the penalty is 0.1, so a 10% penalty, you'll see something sort of like this, which sort of still fits our general shape that we're looking for with a little bit of a bend going towards infinity. And as I increase the bias, the penalty factor, K, you sort of see that there's more and more benefit or reward for being close to the, having a tight inequality, being close to the decision boundary. Cool. One more, something that sort of makes this come together is how do you then deal with the logical connectives? What do you do with the ands and the ors? And there's a natural interpretation called T-norms and T-conorms, which comes from fuzzy logic, which give you an interpretation that basically interpolates between the binary values and gives you meaningful smooth values for things you would get for like what is the and of a 0.8 and a 0.6. And so this plot on the left sort of gives you a visual graphical representation of what that sort of looks like. Importantly, it's at the edges aligns with what we expect from discrete logic, and then in the middle, everything is smooth. And correspondingly, there's a T-conorm as well, which essentially you can just get it via De Morgan's law. I just realized that this figure is not quite correct. It's supposed, there's multiple T-norms and T-conorms, and technically it's supposed to be a round, which is sort of inversion of this guy, but cool. So just to take a pause and just see what we have so far. Given we have an interpretation for the arithmetic components that's smooth already, and then we can augment it with these inequalities and equalities, and then additionally combine everything together with the interpretation of ands and ors, and everything is still smooth. We can essentially punt it into a neural network and be able to learn weights that correspond to the invariant we're trying to learn. In particular, here we'll go into more detail about how you learn the logical structure in a second, but first, just given a fixed logical structure, what's left, can we learn the coefficients on these atomic clauses? And so these are the W's in this particular function f. So what would we do? Given the interpretation for these computational graph nodes, we give it data and take advantage essentially of the neural network like learning process to train weights that will always give you 1, because there's certain invariants give you 1 for the observed data points. And in this case, we get these weights of 1, 1, 1, negative 1, and then those weights would then be subbed into F, and then you can send that off into the SMT solver, and you have a loop invariant. I'll hand it to Jianan to continue from here. Also can take questions if there are any.
So what was the big F? Was that like a template?
Mm-hmm. Yeah, so in this situation, it's a template, but
okay.
So go into some more detail about how you can flexibly learn. Yeah. Cool. Oh, hello, Jianan, are you still there?
Hi.
Cool.
Okay. Can we just go back to the last slide?
Yeah, absolutely.
Yeah. Here we assume that we already know that the correct invariant is say a disjunction of two equalities. And actually this is what we do in the first paper, in the ICLR paper. So we just iteratively try the templates. So first a conjunction, then a disjunction, then maybe conjunction of disjunctions and disjunction of conjunctions, and so basically from simple templates to complex templates. And then we realize that for large formulas, this may cause a problem. And in the PLDI follow-up work, we introduced so-called gated T-norms and gated T-conorms. So here is a definition of a gated T-norm. So we can see that it takes two inputs, X and Y, just like a normal T-norm. But also it takes two gating parameters, G1 and G2. So these are all between 0 and 1. So if we can see that when both G1 and G2 are 1, so when both G1 and G2 are 1, it becomes a normal T-norm, just X, Y, just X and Y. But when G1 is 0, the first term is ignored. The first term becomes 1, and since this is a T-norm, it is ignored. It's just Y. Only the second input exists. And when both G1 and G2 are 0, then the entire thing is ignored. It always outputs 1. So a gated T-norm allows the input to be turned on and off according to the gating parameters. This allows great flexibility. And also this can be, wait a minute. This can also be extended to say 3 inputs, 4 inputs, as long as you have 3 or 4 gating parameters. This makes great flexibility for our framework, because we can allow redundant inputs in our system, and later it can be ignored. And the next slide, please. Yeah, here we show an example. So here the plus means that the corresponding constraint is activated, or the corresponding G is 1. And negative or minus here shows that it is turned off or it's deactivated, meaning that its gating parameter G is 0. So if after the training we get such a framework, we get such a network, then we can extract the learned invariant. And then the learned invariant is, the next slide. Yeah, it's this. So it's a conjunction of disjunction. And the third equality, 2x plus y plus 1 is 0, is ignored. It's turned off because it has a 0 gating parameter. And then the question is, how do we turn it on and off? Actually, this is decided by the training data. So if the training data says that 2x plus y plus 1 is 0, it's not useful, it's not needed, then we will turn it off. So there's a mechanism in how to train the gating parameters G, G1. So basically in this case, our framework, our network can have some redundant terms or redundant structures. And using the data, we can learn exactly what the logical structure should be. And yeah, so this is our overall GCLN model. So we have some inputs, we have some dropout, which we probably don't have time to talk into detail now. And then we have the Gaussian activation and PBQ unit for equality and inequality, basically turn the input to 0 to 1 truth values. And then we have the gated disjunction layer and gated conjunction layer. So they can be redundant. And later we'll learn which atoms or which constraints are useful or not. And using this, we have our overall invariant inference engine. So as we mentioned before, we have the source code. We execute the program to get execution traces. Then we feed these execution data into our invariant inference GCLN model to generate a candidate invariant. Later, it will be verified using the Z3 solver. And if in this case, the Z3 tells us, sorry, you get a wrong invariant, then we need to enlarge the sampling space and retrain the model and try again. Yeah, I think that's what we have now. And now I'll talk about the evaluation.
I had a quick question
Okay.
about, so I'm curious about the optimization itself. Like in practice, does it always go down to 0, the loss or something? Like what kind of loss do you use and how does it behave in practice when you're training there?
I'm not sure if I understand it correctly. You want to ask how G1 and G2 is trained?
Yeah, it's both for the non-gated thing that you had earlier and the recent developments you've introduced in your latest paper. So what is like the loss function, and does the optimization always like bring down the loss to 0? Or?
Yeah, I see. The optimization is just we want the output to be always 1, because maybe we can go back to, let's see where we should go back. To some page when we can show 0 and 1. Maybe far. Yeah, those, yeah, this kind of, yeah, this picture. Actually, on the right, we can see that 1 means satisfied and 0 means not satisfied. So basically, you can think that when something is satisfied, then we define a truth value, then the truth value is close to 1. And our overall optimization objective is we want all the data, every sample, to output 1 after going through our network.
So I'm just wondering, like, does it come to the perfect solution every time, or are there like minor differences or epsilons that you have to consider while extracting the solution? Does it always go to the global optimal? Does it always reach the optimal solution?
Yeah, actually, in the ICLR paper, we proved that if our model is linear, so basically the environment we try to learn is linear, and using our equality Gaussian activation, we can always, so every local minimum is a global minimum. So we don't get trapped in the local minimum. But sometimes we do get trapped. I mean, trapped is not a good word, but sometimes we learn not very useful invariants. For example, we want to learn a conjunction, maybe, for example, x equal to 1 and y equal to 2. That's a very trivial thing. And sometimes we turn out that the 2 units are both learned to x equal to 1. So we learn x equal to 1 and x equal to 1. So sometimes we have this kind of problems, and we have some regularization to make sure that it always turns out what we want. And also there are some numerical errors issues. So basically, if sometimes the input program variables span a very large space, and then it has difficulty learning the invariant. We have some other, say, tricks to fix these issues. And we talk about them in the PLDI paper.
Sounds good, thanks.
So I also have a question, actually. So is there a form of the invariant that you guys are learning? So for instance, like we have seen Boolean ones. So do you guys deal with anything about like quantifiers, for example?
That's a good question. So we have work that is under submission right now that sort of gets a first stab at this would be basically universally quantified over data structures, mostly like in practice arrays. And we have some promising results in that direction, but we'll not talk about them maybe afterwards in AMA or something like that for double-blind reasons.
Okay.
Yeah, actually, that's a very challenging problem. And we can see that quantifier-free invariant learning is, especially linear invariants, is pretty much a nearly solved problem.
Right.
And when there's quantifiers, even simple universal quantifiers under arrays, it's still very challenging. You can see very active works on there. Still, many problems cannot be solved.
As we can continue, if there's not any more questions.
So the evaluation. So we test our framework on basically two benchmarks. The first is CLN2INV dataset. So CLN2INV is a neural network-based invariant inference tool developed by the University of Pennsylvania. And it gets I think it gets a NeoIPS spotlight 2 years ago. It's a very impressive work. And we test our tool on their data set. It has 133 problems, and 9 of them are theoretically unsolvable, so we just ignore it. For the 124 solvable problems, we solved them all. And this big improvement over the previous state-of-the-art CLN2INV and loopinfgen, as we can see here. And we are much faster than them. And here we can see that compared with the other methods, we solved much more instances in a much shorter time. And it's worth noticing that CLN2INV here, when the number of instances solved is 0, it takes some time. Basically means their model needs pre-training. And our model is also neural network based, but we don't need pre-training. So we have one model for each problem, for each loop, and we just train it from scratch. And we also evaluate our improved version, that's the PLDI version of our work, on the NLA polynomial invariant benchmark. That's basically nonlinear problems. And we can solve 26 out of 27 problems, 3 more than the previous state of the art. And our average runtime also small compared to other methods, 53 seconds. And that's all for our work. Justin, do you have anything to say more?
Oh yeah, thanks for listening. And if you have any questions, feel free to ask them.
Great talk.
Thank you.
One question about the evaluation. Did the prior work also use dynamic traces?
So the CLN2INV, I believe, does bootstrap with some dynamic traces. And then loopinfgen is based on a counterexample driven learning. And so there's also it'd be interesting to look at also sample efficiency and stuff like that, but we did not consider that.
Yeah, the time for sampling. So basically generating execution samples is included in our evaluation.
Okay, cool. Yeah, this is very, very cool work. Yeah, very, very neat little, like the transformation into the differential problem is very interesting.
Thanks.
I have a quick question. Thanks for the talk. It was very interesting. What was your insight or intuition, especially in the architecture that you used dropout? What was the reason?
Actually, I have some backup slides that. So by dropouts, we, especially in the case of nonlinear invariants, we essentially just blew it up using the polynomial kernel. And so it'll give you a ton of terms, but the nice thing is you can still feed it through the same general framework to learn the coefficients. And as you can imagine, given some assumptions about depth, of course, and then there's also some terms you can throw out automatically based on sort of just like pre-processing. But you're still left with a lot of terms, combinatorially number of terms. And so one trick we use that sort of speeds up the learning is to randomly include which terms, or sort of call it dropout, but it's not really dropout in the traditional sense from machine learning. And this sort of random mask, if you will, sort of makes the learning a little more tractable. And then if it doesn't learn, or the wrong terms got thrown out, then sort of by randomization running it again, those odds eventually are you'll find a correct answer.
Thanks, that explained it. Thanks.
So I had a quick question about the benchmarks that that you removed from the benchmark set.
Mm-hmm.
So you said they were, or yeah, can you just repeat what why they were removed?
Yeah, so the overall benchmark, also like in the grander scheme, you should also be able to determine if something's unsolvable. And so just to sort of like provide the ambiguity, there's a total of 133 problems, and then only 124 of them actually have invariants. And so sometimes, like if you have a case where the postcondition actually is false, there exists a counterexample to the program, then there is no invariant that's ever going to prove the postcondition true because the postcondition is indeed false. And there's some red herrings that, for their purposes, they've thrown in to sort of, help with their learning process or whatnot.
Okay, so just the ones that don't have the solution.
Yeah.
And so this all comes from the Code2INV paper. Did you look at any of the like Cygus benchmarks for loop invariants, or try any of the tools on like the Cygus side of things?
Mm-hmm. Yeah. So the engineering effort necessary to like go into interfacing into Cygus is a little bit more than we have yet had time to get around to doing. But we have started like there's like a half-built implementation that starts to interface with that. So
Cool.
I guess results TBD.
Awesome. Thanks.
Cool. There's something we also sort of going back to Rohan's question earlier. So sort of concerning the question of sampling, this is something that's part of a trick, I guess, that we use for the PLDI, is that sometimes, for example, for polynomial invariants especially, it's easiest if you get data samples that sort of tell you what's happening between 0 and 1. So the easy place to distinguish polynomials. But most programs that you execute that are going to have like this polynomial behavior won't actually have, for example, in this case, there's never a situation where you can actually like get a sample that sort of represents that intermediate space. And so one thing we introduce is fractional sampling, which is just like a sampling technique that starts the execution at essentially values that violate the precondition, and then sort of executes, and you get these data samples, and you sort of learn invariant that is with respect to different starting conditions. And then afterwards, you can specialize it again to fill in the true initial conditions. So to sort of more precisely, sort of saying that again, well, duplicate slides, but if you can have an invariant that has a given B0, you can learn an invariant based on those variables. Then if you can learn an even more general invariant that doesn't make assumptions about the initial values, then at the end, you can substitute back in the indeed true initial values into that invariant, and then be able to get a more specific invariant. And we use this technique to help with sampling issues related to polynomial invariants. But yeah, we also have some other ideas that haven't been fully realized yet. Cool. But yeah, our code's available online if you want to poke around. Are there any more questions? Cool. If not, thanks for listening.
Thanks again for the talk.
Yeah, thank you for the talk.
Thanks. It was great.
Thanks so much.
Thank you.
Yeah, so we have a little bit of time.
So you can
left,
probably
so-
stop recording.
Yeah, there we go. That's a good idea.